Okay, class. So last meeting we discussed the steady state device nozzles and diffusers. Okay. And for today, supposedly we were supposed to discuss turbines. Another term for turbine would be an expander. Okay, because basically as the fluid passes through the turbine, it expands. You'll see later on why. A turbine is actually excuse me, a series of nozzles. As you can see here, it consists of alternate set of nozzles and rotating blades. So, anong nangyayari dyan ay madaming nozzles. So, may gas na nagpapass through sa nozzles so that yung internal energy ng gas ay nagiging kinetic energy. Okay? Diba yun yung actually equation ng nozzle, pero delta H kasi yun, but we know that through the definition of enthalpy, no? So yung internal energy naka-convert to kinetic energy, so it produces a high velocity stream, and yung mga stream na yan, yung nozzle na yan, nakatapat actually sa mga blades. So anong nangyayari, nagro-rotate yung blades yun. Okay. So, nagro-rotate yung blades. And then, that set up nozzles and blades, that would be your turbine. Okay. So, yan. The high velocity stream can be made to impinge on a turbine blade as to provide a force to move the blade. So, yun, yung force ng high velocity stream exiting the nozzle would move the blade. Okay. So, in essence, yung stream na yun, it does work at the expense of its kinetic energy. Therefore, the effect would be a conversion of the internal energy of a high pressure stream into shaft work. Let's see the equation of energy. Okay, we begin with the steady state energy balance. Okay, so that would be delta H, delta PE, delta KE times mass of flowing stream equal to heat plus work shaft. We can assume that the potential energy is negligible. Okay. And then we can also assume that the kinetic energy is also negligible. Right? So why we can since the inlet and outlet pipes are sized to make the fluid velocity roughly equal. So if the fluid velocity in the inlet and the outlet is equal, then yung delta kinetic energy would be 0. We can also assume a very efficient turbine such that yung there would be no heat loss to the surroundings. Okay, so walang Q, so 0 na rin. And our energy balance would be simplified into work shaft equal to delta H. Okay. So, yung delta H ng flowing stream, yan, mako-convert into the work shaft. Expanding delta H, diba, it's just H2 minus H1. So, that means we need to know the conditions at the outlet and the conditions at the inlet to know yung enthalpies nun. Okay? And once we get the enthalpies, we can just subtract H1 from H2 in order, and then multiply with the mass flow rate to get the work shaft. Okay. Normally, the inlet conditions would be known. Okay, and the discharge for turbines, normally the discharge pressure is known. So, the usual problems would be H1 is known kasi nga you can read it from the steam table using T1 and P1 as the parameters, and the unknowns would be the work shaft and H2 or the enthalpy at the outlet. The way we can solve it, so one way we can solve it is to assume isentropic expansion. So, diba, from ChE 142, there are two conditions so that we can have an isentropic process. One is it should be reversible and it should be adiabatic. Okay? So, pag ganon, diba, if isentropic, then delta S is 0. There's no change in your entropy. It remains the same. So that our turbine undergoes isentropic expansion. If that's the case, we would have isentropic work. So, another term for this would be, for an isentropic work, is the ideal work. Kasi nga, yun yung ideal conditions. Okay. So, pag ganon, diba, we designate yung isentropic work and isentropic delta H, merong parentheses and then sub S sa labas. So, yung work shaft na isentropic, meron ding parentheses and then sub S sa labas, to differentiate it from the actual delta H and the actual work shaft. If we have an enthalpy versus entropy graph, okay, so yung enthalpy yung nasa y-axis, entropy yung nasa x-axis, and we have isobars, we have P1 and P2. So this process would be itong A to B prime would be an isentropic process. Okay, kasi diba yung same siya ng S sa A at S at B prime. So kasi nga nasa vertical line siya, so the entropy is the same. Okay. Now, delta H nun, of course, would be HB prime minus HA. Yan. So, that would be the delta H sub S. Kasi nga, A to B prime is the isentropic process. Now, if we have an actual process, lagi, diba, for in real life, lagi yung entropy is increasing. Papunta tayo sa higher entropy. Therefore, in real life, yung actual, yung B, yung point 2 or yung final, yung outlet, ngayon do sa process, nandito siya sa higher entropy. So that, yung SB mo, or entropy at B minus SA, may value siya. It's positive. SB minus SA is positive. And yun, that would correspond, okay, yung delta H actual mo is HB minus HA. So, anong mapapansin mo? Okay, zoom ko. Anong mapapansin mo sa delta H actual versus delta H sub S or delta H ideal? For a work producing process like a turbine, diba, it produces work, yung ideal delta H is higher. Okay? It's higher than the actual delta H. Meaning, dun sa ideal scenario, pag yung turbine mo ay nasa ideal scenario, which is yung isentropic, okay, mas madami siyang work na napoproduce compared sa isang actual scenario or real life scenario. Okay? So, therefore, nakalagay dito, since equated na yung delta H sub S sa work shaft S, yung delta H actual sa work shaft actual, so therefore, yung work shaft na isentropic is greater than work shaft actual for a turbine. Yan. And we can say that the work shaft produced in an isentropic expansion is the maximum work that can be obtained in a turbine operating adiabatically. In maximum work in the sense na hindi talaga natin siya ma-achieve sa real life, in real life, kasi nga iba, hindi naman possible ang isentropic in real life, pero we can approach it. It's the maximum work na we can approach, but never equate to, hindi natin siya talaga ma-achieve. Siguro sa far future, pag makagawa na tayo ng super efficient na turbine na isentropic siya, no? Pero right now, ano lang siya, we can approach it. Actual turbines produce less work kasi, anong reason? The actual expansion is irreversible. Diba? Yung isentropic kasi, it's reversible, Q is 0. Pero in reality, yung actual expansion is irreversible. So, because of these irreversibilities, may mga friction, may mga losses, yung work na napoproduce ng actual turbine, yung actual work na napoproduce niya, okay, is less, okay, than the isentropic work. Ayun, so doon na papasok yung turbine efficiency. So we rate turbines according to their efficiency. So we compare the actual work of the turbine with its isentropic work. So ang equation ng efficiency ng turbine ay work actual over work isentropic. Or since equated naman sila, 'di ba, yung work shaft at delta H actual over delta H isentropic. So ano siya? Question. Less than 1 ba siya? I mean, makakuha ka ba ng greater than 100%? Or lagi siyang less than 100%? Yung efficiency ng turbine ay laging less than 100%. Bakit nga ulit? Kasi nga, laging mas malaki yung isentropic work or yung work ideal kesa sa actual work for a turbine. Okay? So, ang usual values of a properly designed turbine, yung efficiency niya, ang usual values would be around 70 to 80%. Okay. Let's try this problem. A steam turbine operates adiabatically and produces 4,000 kilowatts. Steam is fed to the turbine at 2,100 kilopascals and 500 degrees Celsius. The exhaust from the turbine is saturated steam at 10 kilopascals. Assuming a turbine efficiency of 85%, determine the mass flow rate of the steam and the quality of the steam at discharge. Let's draw. Let's start by drawing the problem. Paano ba ang shape ng turbine dito sa PowerPoint? Okay, yan. Yan. Yehey! May turbine. Tapos, arrows. Okay, inlet. And then outlet. Okay. Then, given P1 equal to 2100 kilopascal, T1 equal to 500 degrees Celsius. Okay. Then, P2 10 kilopascals. And then, meron ka daw may work shaft na napoproduce 4,000 kilowatts. And efficiency, yan, 85%. Okay. Sabi rin sa problem na ang paglabas niya, saturated steam siya. So, ang condition dito ay saturated steam. Ang required ay, so, given required mass flow rate and quality at the discharge, or X2. Okay? Sige. So, from the steam table, use the conditions using conditions 1. Okay, so yung P1 and T1 from the steam table, makikita nyo dalawa yung given, so most probably it's superheated, but always check. Okay, always check. So ito ay galing sa superheated properties. Pressure equal to 2,100 kilopascal and temperature 500 degrees Celsius. Yung H1 ay 3466.2 kilojoules per kilogram. And then yung S1 ay 7.4087 kilojoules per kilogram Kelvin. Okay? And the first thing that we can do, kasi di natin alam, saturated steam na 10 kilopascal. So, mababasa din pala natin yung HL or yung enthalpy na liquid. Okay, enthalpy ng liquid portion ng saturated steam at saka enthalpy ng vapor portion. Kasi nga, isa lang naman yung kailangan dahil saturated steam siya. Ang problema, hindi natin pa rin masosolve si H kasi wala tayong quality. So, hindi natin ilang fraction, okay, yung vapor part at saka ilang fraction yung liquid part. Pero, given tayo nung efficiency na 85%. So, ano yung pwede nating gawin para makalculate yung H2. Okay? So, teka lang. Bago yun, bakit natin kailangan i-calculate yung H2 muna? So, before this pala, kailangan mong mag-general energy balance. Insert, taga, symbol. Insert, yun. Diba, energy, general energy balance. K. Delta H plus delta PE plus delta KE times mass of flowing stream. Ito nga pala ang dapat mauna sa lahat ng solutions. Okay. Then, diba, kanina dinerive na natin to. We can assume na negligible itong mga to. Negligible kayo. Alis na kayo dyan. Yan. So, ang natira sa equation ay delta H times mass of flowing stream tsaka yung work shaft. So, ano yung unknown sa atin? Kasi itong required sa atin, mass of flowing stream. Ano yung known at unknown? So, yung work shaft, given na yan. Kaya, ayan, no, given siya, 4,000 kilowatts. Ang unknown, yung delta H. Now, kaya natin nga, binasa na muna yung H1 kasi nga, delta H equal H2 minus H1. So, H2 na lang ang kailangan. Yon, na hindi pa natin nga alam dahil wala tayong quality ng steam, ng saturated steam. Pero, gamitin natin yung efficiency. Kasi, di ba, efficiency ay equal sa efficiency ay equal sa delta H actual over delta H ideal or isentropic. Okay? So, wala tayo meron tayo nito meron tayo nitong efficiency. Ang problema pala ay wala tayong hindi pala natin siya agad magagamit. Later pa pala. Sige, erase. Okay. Sorry. Sige. Okay, sige. Pero, lagay na lang natin dyan siya. Park natin siya sa gilid. Save ko muna to. Baka mawala. Yan. So, ang una nating pwedeng gawin ay mag-assume tayo ng isentropic expansion. Sa S natin kunin yung magagamit din pala natin yung efficiency. Okay. Sa S natin kunin yung X mamaya. So, if isentropic expansion, pangalanan natin siya ng S2 prime, 7.4807 kilojoules per kilogram Kelvin. Pareho siya. Diba? With S1. Okay. So, from the steam table kasi, sa conditions na 10 kilopascals, dito sa conditions 2, paglabas, meron siyang saturated vapor entropy equal to, so from steam table to 8.1511 kilojoules per kilogram Kelvin. Hindi ko nalalagay yung unit, basta yun. Okay. And then, meron din siyang S sub L. Okay, yan yung liquid. Okay. Entropy ng liquid, mas maliit, mas hindi siya magulo. 0.6493. Mas maliit siya. Okay. Yung liquid. Yan. So, dyan mo makakalculate yung x mo. Okay, dyan mo makakalculate. Pero, hindi pa siya yung x sub 2 talaga. Kasi, ang nag-assume ka pa lang ng isentropic. So, x quality siya ng isentropic expansion. And, name natin siya na x prime. Okay? Okay, sige. So, ano ba yung natin, yung equation natin, di ba? S equal to SV times X, yan, prime, sa ngayon, plus SL times 1 minus X prime. Okay, plug in natin yung equation, sorry, not equation, values. Yung S, so ito gawin natin yung S2 prime. So, S2 prime mo ay 7.4087. SV mo ay ito, times X prime, plus SL mo ay ito, times 1 minus X prime. So, masusolve mo, isa na lang unknown, masusolve mo si X prime. Okay? And X prime is equal to pag ginamitan mo ng calcu yan, 0.9010 yung quality niya if, very big if, isentropic expansion. Okay? So saan mo yan magagamit? Anong silbi niyan? Mamaya, magagamit din natin itong equation na yan. So, meron kang quality prime, x prime. Solve mo ngayon yung H2 prime. So, ano ba yung H2 prime? Yung enthalpy niya if isentropic expansion siya. Okay? So, ano bang equation nito, diba? HV times x prime if lahat nito if isentropic, HL times 1 minus x prime. Okay, so plug in natin ang values. Ang unknown dyan, di natin alam yung H2 prime. HV, okay, galing sa steam table. Okay, galing sa steam table, didiretso na. Pero like I said, galing yan ng steam table. Kilojoules per kilogram. Yan, 2584. Times yung x prime na na-solve kanina, 0.901. Okay, plus, ito ulit galing sa steam table, 191. Yung HL, na binasa at 10 kilopascals. Okay, times 1 minus 0.9010. Okay. So, masusolve mo na si H2 prime. H2 prime is 347.98 kilojoules per kilogram. 2347.98. Okay? Yan. So, dyan na natin magagamit itong equation na to. Sige. So, paano? This is equal to H2 actual minus H1 divided by quantity H2 prime okay, minus H1. Okay, bakit? Kasi nga, diba, yung nasa ilalim ay na-OC ako. Gusto ko rin ng malaking sign. Yan. Diba nga yung nasa denominator yung delta H isentropic. So, instead of yung H2 actual, yung H2 prime yan. Okay? So, known yung H1, known yung H2 prime, nasolve natin. Known na tong H1 dito. Known to, given yung efficiency. Ano na lang, unknown. Yung H2. Okay? Or pwede mo pala i-retain na lang to na delta H kasi yun naman yung gusto mo. Okay, yung delta H. Yan, delta ka. Delta H actual. Okay, yun na yung unknown mo. Okay, sige. So, delta H ngayon ay rearranging the equation H2 prime minus H1. So, this is yung given na 0.85 or 85% times yung na-solve na H2 prime minus yung binasa sa steam table na conditions na H1. Okay. Ang masosolve mo dyan ay negative 950.487. Tama ba na negative siya? Tanong, tama ba na negative siya? Ang delta H for turbines, delta H equal to work shaft. Delta H times mass of flowing stream equal to work shaft. So, ibig sabihin, pag negative yung delta H mo, negative din yung work shaft. Tama ba yun? Tama ba? Tama yun kasi work shaft done by the system. Diba? Work producing siya. Work producing yung turbine. So, work is done by the system. Palabas yung work. Kaya negative. So, tama yung ginawa mo pag ganun. Okay. Ano ba yung unknown? Yung mass of flowing stream. So, ito ay kilojoules per kilogram. So, calculate na natin ngayon yung mass of flowing stream. Diba? Delta H. So, balik na tayo sa general energy balance. Na-simplify na nito. Equal to work shaft. Okay? So, therefore, mass of flowing stream is equal to work shaft divided by delta H. And alam mo yung work shaft mo kasi given yan. It's 4,000 kilowatts na dapat, okay, negative. Hindi mo nilagay kanina, pero dapat negative kasi work done by the system. Palabas nga, o, diba, may arrow dyan. So, dapat negative yan. So, negative 4,000 kilowatts. In other words, kilojoules per second. Okay, so negative yan. And then, di-divide mo yan do sa delta H na nakuha mo, na-solve mo kanina, delta H actual, na negative 950. Sige, divide mo yan. Okay. So, ano ang magiging unit? Una, anong magka-cancel pala? Magka-cancel yung negative sign. Yan, cancel yan. Magka-cancel yung kilojoules. Yan. Ayan, iksi kasi. Yan. Kilowatts nga ba? Yeah, kilojoules. So, ang matitirang unit kilogram per second, which is tama, yun ang unit ng mass flow rate. So, magiging, ang makukuha mo dyan ay 4.21 kilograms per second. Yan. So, isa na yan sa required no fill. Yan, isa yan sa required. Okay? Tapos, ang isa pang required ay yung X2. Ay X2. Or, dito pala x2 prime yan. Pero basta ganun, x prime na lang. Basta siya yung x prime paglabas sa point 2 sa outlet. So, ang hinahanap mo yung x actual. Pag yung quality niya dito, paglabas, pero actual, hindi yung prime, hindi yung sa isentropic expansion. So, paano mo yun masosolve? Kailangan mo yung either yung S2 actual or yung H2 actual. Yun ang kailangan mo. Pero, since ang masosolve natin na mas mabilis ay yung H2 actual, bakit? Kasi nga, meron tayo nitong equation na to, di ba? Yan. Pero ito, gawin natin H2 actual minus H1. Then, isolate mo yung H2. Isolating H2. Or ito kaya, gawin na natin ng delta HS. Kasi meron na tayo nung hindi. Retain na lang. Basta, i-isolate mo yung H2. So, paano yun? N times ito plus H1. Tama. Parang may mas madaling method dito. Ang mas madaling method is delta H actual. Okay, delta H actual plus H1. Yun. Kasi ito nga pala, itong quantity na to ay delta H. Diba? This quantity here, this is delta H. At ito, hindi to divide. Multiply yan. Yan. Diba delta H to? So, palitan natin to ng delta H. Okay. So, may value na tayo ng delta H kanina na yan, negative 950. Plus, may value tayo ng H1. H1, where are you? Ito. Okay. So, therefore, ang H2 mo ay 2515.713. Yan ang H2 mo. So, masosolve mo na ngayon si X. Kasi, ito lang siya. Where are you? The equation. Ito. Okay, copy-paste natin. Tanggalin ang mga prime. Oops. Yan, di ba? Same lang siya. Tanggalin ang mga prime. Palitan, i-substitute yung values. So, H2 is alam mong 2515.713. Equal. Alam mo yung HV. What is HV? Ito na nga. Copy-paste ko. Tapos palitan ko lang ng X to. Okay, X. Yan. Then, solve for X. Okay, solving for X. X is 0.9711. Yan. Use your calculators. Okay. Nakailang minutes na tayo. Saan yung time? Walang time. Anyway. Ayun, 39 minutes. Sige, so, dyan muna. Okay. Ano pa bang? Hanggang dyan na lang muna kasi masyado nang mahaba. Ang recommendation is 15 minutes lang kada session. Yan. Ito. So, ito ang homework nyo. Try to solve on your own. Okay. Gagawin ko na lang siyang multiple choice para pwedeng individual work. Sige. Okay, see you next lesson.